1958, Norman Gilbreath published this in the linking ring. He sent them a letter containing some magic tricks he had developed. And they really came to the public when Martin Gardner wrote about them in his mathematical games. It's a trick involving alternating red and black cards. And I'm going to really give the trick away here. You start off with the deck already in alternating red and black. You hand the deck to somebody in the audience, ask them to cut the deck, pass it on, cut the deck, pass it on. And at some point you ask somebody to bring the cards up and count it out into two piles, dealing off the top of the deck. And then you shuffle the two piles together, and what you, the magician, then do is show them that you can actually pull out cards in alternating colors. So what happens is your original order, the deck is set up in red, black, red, black. Cutting the deck doesn't do a thing. That's just a little audience participation. And when you deal off the top into two piles, you still have red, black, but notice that one pile goes one direction, the other pile goes the other. One starts black, and then red, and then red, black, black. And then it's a proof by induction that no matter how you shuffle the cards, once you put the deck back together, if you pull the cards off two at a time, what you end up with are alternating pairs of red and black, one of each. We can turn this into a mathematical problem by saying instead of the cards, take the numbers, in this case 1 through 10. We'll do away with the cutting. That really had nothing to do with anything. And then dealing off the top of the pile of numbers to make two piles here, and dealing off the top, I get 1 on the bottom through 4 at the top. I then take my two sets of numbers, shuffle them together, and I get 5, 4, 6, 7, 3, 8, 2, 9, 1, 10, which is what's called a permutation of the set. So a permutation of 1 through n, that's just a reordering. The notation usually is pi for permutation, and pi of n is the value in the nth position. Now there's lots of permutations out there. If you have n numbers, there's n factorial permutations. There's nowhere near as many Gilbreath permutations, which, as it says, is one that arises from this trick. So the natural question is, how do you know when a permutation is a Gilbreath permutation? And we have here what's referred to as the ultimate Gilbreath principle. There's a lot of stuff up here. But what I'm really interested in is down at the bottom here, number 4. For each j, the first j values are consecutive in 1, 2, 3, all the way through n. Now what I mean by that is this example here, 4, 4, 5, 4, 5, 3. They're not in order, but they are consecutive in 1 through 6 here. So 4, 5, 3, 4, 5, 3, 6, 4, 5, 3, 6, 2, and then finally, of course, 4, 5, 3, 6, 2, 1. That's all consecutive in 1 through 6. So that is a Gilbreath permutation. Now, when I learned about this, I thought it was fun. I thought it was interesting. I bored my students to tears by repeatedly forcing them to watch this. But at the time, I was writing a book on Kenner sets, working on a chapter on continued fractions. So up top here is a finite simple continued fraction. Simple meaning that all the numerators are 1. On the bottom, I have an infinite simple continued fraction. And because all the numerators are 1, the only thing I really have to worry about are the denominators, a0, a1, a2, so I get the shorthand notation. And what occurred to me is the notation for the continued fractions is almost kind of the notation for the Gilbreath permutation. And so my question was, what kind of continued fraction do you get from a Gilbreath permutation? So a finite Gilbreath continued fraction is a fraction of the form 0, colon, a1, a2, all the way out to an, where all those a's come from a Gilbreath permutation of 1 through n. So the permutation 3, 4, 2, 1 becomes the continued fraction 0, 3, 4, 2, 1, or writing all that out using fraction notation there, well, use the dot, there it all is. After finite continued fractions, you get the idea of infinite continued fractions, and all I need to do is straighten things out. So once I get to the 5 here, 6, 7, 8, 9, that's just in regular order. Being a mathematician and an analyst by nature, my first question is, well, what do you know about this in the unit interval from an analytical point of view? It's a closed set. It's nowhere dense. There's as many Gilbreath continued fractions as there are integers, and it's a scattered set in the interval, scattered being a really esoteric, most analysts don't know it term. There are a few things we do know about this. They're related to the Bessel functions, because it turns out that this continued fractions just goes 1, 2, 3, 4, on, is negative I times j1 of 2i divided by j0 of 2i, where I is the square root of negative 1. And so we actually know the value of that Gilbreath number. And from there, we can kind of go off to the other infinite Gilbreath continued fractions. There's, of course, more decimals, periodic ones. So rather than straightening it out, going 6, 7, 8, 9, dot, 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 I can just keep repeating the permutation over and over, along with some generalizations of it. So what we have here is a lot of times there's a math principle that goes to a magic trick. This time a magic trick going to a mathematics principle. 1, 0, thank you.